Welcome back. In the last video, we covered the basics of programming, what it is, how computers understand code, and how that code becomes a running program. So today in our module 2, we are stepping back before we touch any code at all, because there is a step almost every beginner skips, problem solving. By the end of this video, you will know exactly how to break down a problem, plan it out with an algorithm, and represent that plan using flowcharts and pseudocode. So we can see what we will cover over this video. 17 topics in total. We will start with what actually count as a computational program, move through analyzing and breaking problems down, and then spend a good chunk of time on algorithms, flowcharts, and pseudocode. Then there are three, and these are the three different ways of expressing the same logic. And by the end, we will even do a dry run together, tracing through an algorithm step by step. So let's start. First, we need to know what is exactly a computational problem. It's any task that can be solved by following a clear, finite set of steps. Something a computer or even a person can logically work through to reach an answer. And every computational problem shares three things. It has a well defined starting point, which is the input, and it has a well defined goal, that is the output, and there is always some process that gets you from the input to that output. And some of the examples for this is finding the largest of three numbers, then sorting a list of names alphabetically, or calculating the total price of items in a shopping cart. All of these fit the same pattern. Something goes in, something happens, and a result comes out. Here comes the problem analysis. Before we write a single line of code, there is a step that absolutely critical. And problem analysis just means carefully studying a problem before jumping into code, really understanding exactly what's being asked. So when you are giving a problem, you should ask yourself a few questions. What I am given, or what am I given? What's my data or my inputs? What do I actually need to find? What's my goal or output? What rules or limits apply? Are there any constraints? And have I seen a similar problem before? And here's the golden rule I want you to remember. Never start coding until you fully understand the problem. It feels slower at first, but jumping straight into code without a plan almost wastes more time than it saves. Then we need to identify the input, process, and output. So every computational problem can be broken into three parts, known as the IPO model: input, process, output. Input is what data we start with, and process is the set of steps that transform that data, and output is the result we ultimately produce. So here we have an example, finding the average of three numbers. Our input is the three numbers themselves, and the process is adding them together and dividing by 3, and the output is the final average. So once you start thinking about problems this way, breaking them down becomes naturally, it will naturally come to you. Then understanding the constraints. This is something that beginners often overlook, and it can really enhance your code later. Constraints are simply the rules, limits, or conditions that your solution must respect. That could be limits on input size or value range, like age must be positive only, age can't be negative. Then it could be time or memory limits, like this must run in under 1 second, or it could be some logical rules, like discount only applies to orders over $50 or something. And why this actually matters? Because ignoring constraints often leads to solutions that work perfectly in theory but completely fall apart on real world. Thinking dividing by zero, or trying to process an empty list. So thinking about constraints early saves you from these some errors or bugs later. Then how can we break a problem into smaller problems? Big problems can often feel very overwhelming, and that's exactly why we break them down into smaller, more manageable pieces. The approach has a name, which is modular approach or decomposition. The idea is very simple. Solve each small piece on its own, then combine the results to solve the bigger problem. So take the example, like we need to plan a birthday party. So on its own, that's a very huge task. But break it down, and suddenly it became very modular, manageable chunks. Sort of the guest list, handle the venue and food, and take care of decorations. Each of these is its own smaller problem you can tackle on its own. So this exact same thing applies to every programming problems too. Then we have step by step problem solving. Once we have understood a problem and broken it down, we solve it by following a clear sequence of steps. And the flow that I have given, first understand the problem, second plan. This is where your algorithm actually comes in. Then actually solve or implement it. And fourth, test and verify that it works. So here what you need to remember is skipping steps, especially the planning step, is one of the most common reasons something a beginner code ends up messy or full of bugs. Good problem solvers actually spend more time thinking than they do typing. So we understood what is a program and how to modularly divide the program into small chunks. Then that brings us to a word you have probably heard a lot, algorithm. So what actually is it? An algorithm is a finite, ordered sequence of well-defined steps that solves a problem of or performs a task. The logic, as I always mention, think of it as the recipe before you write any actual code. And an algorithm is language independent. With the exact same algorithm could be implemented in Python, in Java, or in C. The logic doesn't change, only the syntax does. So why do we even need algorithms? The reason is they let us plan and verify our logic before coding. They make problems much easier to explain and debug. And they can actually be analyzed for efficiency and correctness, which becomes really important as our programs grow. Then what is the characteristics of a good algorithm? Not every set of steps qualifies as a good algorithm, of course. Then there are specific characteristics that define one. First, it must be finite. It has to end after a limited number of steps, and it must be definite. Every step needs to be clear and unambiguous. It needs input, zero or more well-defined inputs, and there of course should be output too, one or more well-defined outputs. It has to be effective, meaning each step is simple enough to actually be carried out. And finally, it should be efficient, solving the problem using a reasonable amount of time and resources. So if you can't clearly explain your algorithm to another person, it's probably not ready to become code yet. So how to write your first algorithm? So here we have some problem to practice, finding the largest of three numbers. Step 1, start. Step 2, input three numbers A, B and C. Step 3, if A is greater than B and A is greater than C, then the largest is A. It is simple. Then step 4, if it is not, if the condition we have given in the step 3 is false, else if B is greater than A and B is greater than C, then the largest is B. Step 5, if none of that condition is true, otherwise the largest must be C. Then step 6, we got a result. Now which number is larger? So display the largest value, and final step, stop. So notice how each step is simple, ordered and completely unambiguous. There is no guessing involved. And this exact same logic could be written in absolutely any programming language you choose. So I have given some algorithm example here, because algorithms aren't just a programming concept, they are everywhere in daily life. Take making tea. Boil water, add tea leaves, wait 3 minutes, strain into a cup and add milk or sugar. That's an algorithm. Or checking if a number is even or odd. Input a number n, divide it by 2, and if the remainder is 0, it's even, otherwise it's odd, and then display the result. So I think you know the logic behind the odd and even numbers. The idea here is that algorithms aren't just for computers. We follow algorithms in everyday life constantly, often without realizing. Then what is a flowchart? So when we visualize an algorithm, it becomes a flowchart. A flowchart is a visual diagram that represents an algorithm using standard shapes and connecting arrows. So it makes the logic of an algorithm easy to take. It uses specific shapes for specific meanings. Start and end points, process steps, decisions, and input or output. And it's especially useful for visualizing the branching logic and loops. So why bother with a flowchart at all? Because even if we have an algorithm, it's often much easier to spot a logic mistake in a picture than in a written list of steps. So flowchart makes the flow of control visible. So which are the flowchart symbols that we use? The shapes that I have given here is different for each steps in our flowchart because each shape has a specific meaning. This oval shape represents the terminal. It marks the beginning or end of a flowchart. So you will see it labeled start or end. Then this rectangle represents a process, some action or calculation step. Then this slanted shape, a parallelogram, represents input or output, reading in data or displaying a result. And the diamond represents a decision, a yes or no branching point in your logic. And connecting all of these, arrow shows the direction of flow, the path your logic follows from start to finish. Hope you understood. So now create our first flowchart. So put those symbols to work and build our first complete flowchart, checking whether here a number is even or odd that we wrote earlier in our previous slide. We start at the oval that says start. Then we move into our input shape, input n. From there we hit our decision command. Is n mod 2 equal to 0? If the answer is yes, we follow that path to the process box that says display even. If the answer is no, we follow the other path to a process box that says display odd. And both of those paths eventually come back together and lead to our final oval stop. So you can see how much clearer this is visually compared to just reading a numbered list of steps. We can literally trace the path our program will take seeing through the visuals. Then we have pseudocode. Pseudocode is a plain, informal way of describing an algorithm using structured, code-like language without following strict syntax rules or any real programming language. So it is actually sits in right in between plain English and actual code. It uses simple keywords like start, input, if, else, while, output, and stop. And because of that structure, it's really easy to translate into any real programming language later on. So here I have an example. If a person's age is greater than or equal to 18, output you can vote, otherwise output you cannot vote. So notice how close this already looks to real code. But it's still simple enough that anyone can read it. So how to write your first pseudocode? So the example that I have given to practice is finding the sum of the first 10 natural numbers. We start, we input n, we set our sum to 0 and set a counter I to 1. Then while I is less than or equal to n, we add I to our sum and increase I by 1. Once that loop ends, we output the sum and stop. And the structure here is input, initialize your variables, loop, then output. So this is a pattern we will constantly see once you start writing real code. And pseudocode lets us plan it out clearly before we touch any actual syntax. So we learned three things: algorithm, flowchart, and pseudocode. So at this point you might be wondering what are the differences, or are these all kind of same thing? So in terms of form, an algorithm is numbered text steps. A flowchart is a visual diagram and pseudocode is a structured code-like text. They are each best for different things. An algorithm is great for explaining logic simply. A flowchart is best for visualizing flow and branching. And pseudocode is best for bridging that logic into real code. In terms of detailing, algorithms are general, flowcharts gives you a visual overview, and pseudocode gets you closest to real syntax. And as for tools, an algorithm needs nothing but plain text. A flowchart needs shapes and arrows, and pseudocode just needs a random text editor. So all three describe the exact same underlying logic. They are just different ways of expressing it, useful at different stages of planning your solution. Okay. So now what is a dry run or test table? So it is last but not definitely not least, the dry run and its companion, the trace table. A dry run means manually walking through an algorithm step by step on paper to check whether the logic actually produces the correct result. A trace table records how your variable values change at each step of that dry run. And it's a fantastic way to catch logic errors before you ever write real code. So here we can trace through our earlier example, summing the numbers 1 to 3, where n equals 3. We start with I equal to 1 and sum equal to 0. After the first loop, I becomes 2 and sum becomes 1. And after the second loop, I becomes 3 and sum becomes 3. And after the third loop, I becomes 4 and sum becomes 6. And since I is now greater than n, the loop exits, leaving us with a final sum of 6. So which is exactly what we would expect from 1 plus 2 plus 3. So the summary of our today's video is, every problem has an input, a process and an output, and you need to understand all three before you start coding. So break big problems into smaller ones and always plan with an algorithm first rather than jumping straight into code. Then flowcharts helps you visualize your logic, while pseudocode bridges that logic into something close to real code. And the dry running your algorithm with a trace table is one of the best ways to catch mistakes early before they become bugs in actual code. So that's all about our module 2. In the next video, module 3, we are finally going to start writing real code and get our programming environment set up. If this video helped clear things up, drop a like, subscribe if you haven't already, and I will see you in the next one. Thank you.